Right. My big contribution. Everything's okay? Shall I begin? Okay, good. So good morning, everybody. We are lucky today to have with us Professor Aquino, Wilkins Aquino from Duke University. He's a professor in computational mechanics at Duke, and he's quite the essence of what computational mechanics is. He's in the Department of Mechanical Engineering and Materials, but he's also has appointments in Department of Applied Mathematics and in Civil Engineering. So which proves that computational mechanics is quite transversal. He has been working in acoustics, in image processing, in inverse problems, fluid structure interaction, many things. And today he's going to talk about one of the topics that he has been working lately. So, please, whatever you want, the floor is yours.
Thank you.
Thank you for coming.
Yeah, thank you, Antonio, for having me. So I took the opportunity that I was going to be in Barcelona and told Antonio that I would like to meet all of you and share some what we have been doing. I came with my family to see a Barca game. So, but of course, you know, I'm an academic. I wanted to come and connect with the UPC. I've been trying to on that. So, okay, so let's get into today's talk. So this, yeah. So I'm going to start with the motivation. Okay, so I chose this topic because there is it's one of the topics that in my career I found where I had a very strong footing on the applications. We had to do a lot of work with the algorithm developments, with finite elements, with computing, getting into the part of architectures and things like that, but also on the mathematical analysis. So we found all of that. This work was in close collaboration with Marc Bonnet, who's a close friend. We've been working for about 15 years together. And he and I always have these pet projects on the side where we work together, sometimes with my students, but many times by ourselves. And the work that I'm going to present to you spans all this time that I've working with Marc. I gave this talk as part of his 60th birthday last year, which was his 62nd birthday, because this was supposed to be in 2020. So not many people have seen this talk. It's a compendium of this technique. But let me start with motivation for some of the work that you're going to see. So we've been, since I started my academic career, working with inverse problems in medical imaging, but a very particular type of problem, which is probing the mechanical properties of soft tissue with the ultimate goal of diagnosing. So you probably have heard this, but if you haven't, basically soft tissue, right, manifests itself, or the presence of disease in soft tissue manifests itself with changes in stiffness or viscoelasticity. Let's say for the mechanicians, that suffices if I tell you. For the if you're not a mechanician, basically the structure of the tissue starts changing way before the onset of disease. For instance, breast tumors, they start appearing as stiffening of the tissue, calcification, and so on. One of the problems that I work very closely, atherosclerosis. Arteries start stiffening up way before you see plaque deposited in there, so on and so forth. So what if we can palpate? We can perform some tension tests, compression tests, to ascertain these properties, right? That will give us a lot of information. Now, we cannot do it, right? So the way to do this is indirect, right? So can we excite tissue? Can we probe it and measure some of the mechanical responses? So I'm going to show you a technique that was developed at the Mayo Clinic Ultrasound Lab in the mid-90s that uses ultrasound in a very unconventional way. When I say unconventional, is you probably are familiar with ultrasound that looks like the middle image here. These grainy images that we call B-mode ultrasound. This is the typical one when we get an ultrasound. The way you produce the image is basically from an ultrasound being mechanical excitation, usually in the megahertz range. You get a scattering from particles and fine structures of the tissue. You get the scatter field back, the intensity of that field, you plot it, and that's what you get. So bright images means strong scatterers, dark, not so much scattering in a fluid medium, right? Like the human body. That's pretty much, I mean, that's an oversimplification for what ultrasound is, but it has most of the essence. Now, what happens if you try to do this to a certain mechanical properties? Well, from mechanics, right, we will know immediately a couple of things. One is what you're seeing there are mostly rigid scatterers, right? So we are not probing really the elasticity of the tissue. Number two, these waves are in the megahertz range, right? So just to give you an idea, a shear wave in soft tissue is in the order of 1 to 3 meters per second of order, right? So if you do the math, the wavelength that you're going to get, all right, just divide that 1 by a million, right? So a micron, right? Roughly speaking. So we cannot use ultrasound very easily to characterize the tissue properties that we're interested in at larger scales. Okay. However, it will be highly desirable to use ultrasound to probe the mechanical properties like shear modulus, plot modulus, in anisotropic materials, all the constants in the elasticity tensor, or viscoelastic properties for diagnosis. Now, to do that, researchers at Mayo Clinic developed the concept of excitation remotely with ultrasound. Not only the scattering, but can we produce a force remotely? Number one. And then number two, once we produce that force, can we launch a wave and then track it with the same transducer? So that was decades of research and development until we got to what I'm going to show you, which is exactly that. Probes that instead of having one piezoelectric crystal to generate those images, the scattering images, that basically you send a wave and listen. One that has hundreds, 100 or so piezoelectric crystals with which we can use ultrasound to generate a force. How do you do it? Well, mechanical wave carries energy. So if we could get the tissue will absorb the mechanical energy. And then once you absorb energy, you change momentum. If you change momentum, there is a force present. So can we use those principles to generate a force now with ultrasound? So yeah, answer is yes. Always you have a force when you have ultrasound. The problem is, can we generate a force with significant amplitude so that we can detect? And what they did was to use that idea. Focus the ultrasound beam, focus the energy, increase in a smaller region, increase the total force that you get, the cumulative force, so that we can now have something that we can detect. Number two, modulate that or do it as an impulse and generate another wave that we can track. So that principle leads to something that has now become an area of research in biomedical imaging. It's called elastography. We can generate a wave, track it, and as we track the wave, we can hopefully reconstruct the mechanical properties, right? So just to give you an idea, so let's take this example. Let me do this for the people that are online. We have here now the same graining image that we had before, right? But now on top of it, we have an ultrasound transducer with 128 crystals. Some of those crystals can be used to generate an ultrasound beam that is going to be focused like this. Well, they say on focus because it's a relative word. It's on focus for the people in ultrasound because they usually focus in a very small area. This ultrasound beam is like a column, and then that's on focus. But based on the principle that I told you, focus enough to generate a force. So you do that, you turn on that beam, the tissue absorbs, and now you launch a wave. The rest of the 120 crystals, through the Doppler effect, we will not get into that, can track particle motion in a fine grid. And this is what you can do once you post-process that image. Same phantom, you get that, right? Now we see a wave propagating. What you see is the vertical velocity, particle velocity at a point, but just the vertical component. So the direction of the ultrasound beam, you can track with enough accuracy the motion of the particle. Horizontally, the field can be reconstructed with some very complicated techniques, but it's very noisy. So for practical purposes, we say we can track vertical components of velocity and displacement, okay? So now, with that information, the question is, can we actually estimate the stiffness of the surrounding medium? Because if we can do that now, we can start getting to information that carries, that can tell us something about disease, right? So that was the premise of ultrasound imaging. This has been extended to basically diagnose different tissues in different organs like the heart, arteries, kidneys, liver. So areas that are in the artery, I say artery, the artery, that's what I say it, but places that are accessible by ultrasound and that are connected to these different diseases that are very important for humanity, right? Cardiovascular disease, kidney disease, liver, right? So some of these machines are already in clinical practice because this area has been around for about 30 years now. France is one of the countries where there's been a lot of research. You can go to clinics where they can do one of these tests and image a shear modulus field, and then use that to, even if they don't image it, get out the shear modulus in a homogeneous medium and stage liver disease with that. There is enough data now for them to do that. That is a whole world on how to generate the data and get the generate the data, right? The post-processing part, this is where we come into play as mechanicians. So as I told you, we have a displacement field or a velocity field. How do we estimate a mechanical property? That's an inverse problem, right? The way that they do it in biomedical imaging is one technique, and they have different techniques. My group has been working on other more sophisticated techniques based on mechanics. The way since I mentioned by how the machines do it at this point that are deployed, very simple ideas about wave propagation locally. Use phase shifts to connect to the elasticity equation. And without getting into the details, you can do these estimates, local estimates of shear modulus. That's what is used in the machine. Now, those techniques, as you can imagine, make a lot of assumptions about one dimensionality of the fields. So you saw here, if you try to image this, you see the scattering, that's not one dimension. So if you try to use one of these techniques, you're going to get a lot of aberrations. So a lot of this talk is, how do you go about estimating, inverting for the shear modulus given this data, or mechanical properties in general? Before I go on, let me clarify something. You're going to hear shear modulus a lot in the presentation. What happened with the bulk modulus? We're going to talk about isotropic elasticity. What happens is soft tissue is like water, right? So nearly incompressible. The bulk modulus, I know what it is. Or for us in wave propagation, what is the speed of sound in what? 1,500 meters per second. That's known. I treat it as known always. What is not known is the shear. So here's what we're going to try to do. We're going to try to estimate that field. I'm going to show you some of the techniques, a very special technique that in my group, we have shown that it has a this protein is a niche for that. So what are the benefits? Why are we doing this, right? Why is ultrasound? Why don't you do an MRI, right? Or use CT scans or something? Of course, those techniques are what you will use for high resolution imaging, right? Nothing beats those techniques in terms of resolution. However, you get the problem ionizing radiation. Ultrasound doesn't have that. CT scan does. In ultrasound, in MRI, portability, right? And cost. So an ultrasound test is hundreds of dollars versus an MRI test, thousands, right? Now, ultrasound comes with a very strong, significant challenges. One, noise. You saw those images, there is significant presence of noise. There are scatterers around that you don't know what they are, and they're going to perturb the field. And here's one of the challenges for mechanicians and for applied mathematicians, that once you start getting into this problem, you will realize there is high uncertainty in loading and boundary conditions. That radiation force, we don't know what it is. We just know that there is a transfer of momentum, but quantifying that is a significant challenge. So one of the things we're going to do, we're going to ignore that force. And I'll show you why we can ignore it, okay? We know very little about boundary conditions. So when I'm imaging a tumor around it, I don't know the surrounding tissue. I just have this window where I see the data. What is at the border of the image? I don't know what it is. Of course, I have the data, but will not be a good idea to use those as boundary conditions because of the level of noise that is in there. Okay, so you strongly enforce those, you're going to be introducing gradients strongly of noise. But actually, everybody has worked with this problem, has tried it. You have to see it for yourself. You're going to static noise from a TV when you do that. Okay, so then the data is dense. You have a lot of points, but it's one dimension. So that creates immediately define the problem for us. We want to do an inverse problem in a medium right? Where we have a lot of data, but you just have one component of this place. Let's stay with 2D, okay? You just have one of the components. Number two, I'm telling you, you don't know the boundary conditions, okay? So you don't know the Neumann conditions, you don't know the Dirichlet conditions here, all right? So you can probably sense the challenge of this problem, right? And then I have noise. With that, we take on the inverse problem, okay? So the way you postulate that problem is as an optimization problem. You say, I have this field, I know the field equations, I have the data. Get me what I don't know in this problem. What I don't know are the boundary conditions, the shear modulus, okay? So can we get all of that from the data? You have a lot of data, it's an entire field. So I just told you, summarize what could have been an entire presentation about that inverse problem, right? So how will you solve that? You very likely will try to do something like this. Postulate the L2 distance, let's call this norms distance, between you, which is the field that I can compute with, let's say, finite elements, right? You postulate your elastodynamics problem. It's a function of bulk modulus, shear modulus. I'm going to, for now, for these cartoons, I'm about to motivate error in constitutive equations. I'm going to consider both of them for now. Later on, both modulus it's no. But you may try to do this. This is at the heart of the presentation, at the heart of the message I'm going to show you. We're using this problem as a motivation. This is the most natural, for us as applied mathematicians, engineers, mechanicians to use. And we say, okay, let's solve this problem. We have this rectangle fixed at the left. It's excited with harmonic load at 400 hertz. It's isotropic. I know that information. I know the density of the material. You get the particle displacements here in one dimension. So, okay, let's estimate actually in all dimensions. And here I assume that I know everything. And say, okay, let's estimate this using this. The way that you postulate this problem to make it efficient is with the Hammond's equation in the frequency domain. So basically, wave propagation in the frequency domain. And I'll show you that these problems will present an immediate challenge for you, which is this. Remember, we're going to solve this problem as an optimization problem. We're going to minimize that, subject to that we satisfy the governing equations. This is what the objective function looks like. Coarsely, I plotted this myself with a coarse grid of material. So that has a lot of local meaning, right? So if you try to solve a problem in the frequency domain, like this, people in seismic imaging solve problems like this, right? They stick to the time domain, as far as I know, talking to some of my friends in imaging a lot. That's one of the issues. That doesn't mean that the time domain doesn't have local meaning. It does. It just doesn't look like this. At the root of this is something very fundamental, right? So when you're in the frequency domain, and the time domain as well, this is physics. There are resonances. Right? So now the resonances, right? There are frequencies where your solution blows up. It goes to infinity, right? I mean, tries to go to infinity, goes unbounded, grows a lot in physically. In mathematics, is your operator now has a null space when I have a resonant frequencies. They change those frequencies, the spectrum changes with the material properties, right? So as I start changing the material, you hit some of those. That's where the peaks are. So you create all these local minima. Even if you have one solution, one global minimum, there are infinitely many not solutions, but local minimum in the problem, right? So that is the problem, one of the problems that you can add to the challenges, actually, of that we have. So even if I could deal with unknown boundary conditions with one field and so on, I still have the problem. So I just want to bring you to this idea of error in constitutive equations that was brought to my attention by my friend Mark Bonnet back in 2009, I think. You can find many names for this. Minimization of potentials, for instance, for inverse problems. You can call it, people call it something related to misfits of in elasticity. I don't remember all the names, but this has been named many things, right? So the key idea, Mark wrote a paper back in 2005 where they did a review of these methods that were confined mostly to France, as far as I can tell. Ladevez was one of the people that started working with this back in the early 80s as an error estimator. So using error estimators for a priori error estimators, a posteriori, sorry, for adaptivity, using the idea, some idea similar to what I'm about to show. For those of you who are here, I imagine some of you are graduate students, people, postdocs, people starting your career. So even if you're senior looking for fresh ideas of how to tackle problems that are open there, I think this idea actually has many potential applications, and it has a very strong fundamental mathematical benefit. So at that time, Mark presented it to me as an idea where they had seen that this convexification, that of convexity issue, if you want, this local minimum, was not present when they tested this, right? He wrote up a review paper where they looked at all these methods, and they looked empirically that they saw that these methods gave them something better. So let me show you what these methods can do, and I'll show you that a lot of those challenges that I presented to you that in mechanics get addressed here. Not by construction. We found this as we work with the method, right? So key ideas. What we're going to do in these methods, instead of postulating the misfit between data and models, just using displacements, we're going to relax things. We are going to actually relax the constitutive equations and treat stresses and strains as independent fields from displacement. Okay? Similar to what happens in mixed methods. Okay? So you will see that actually I get to a mixed field formulation in the end. And we are going to enforce the measurements, not as strongly as the Dirichlet conditions, but through a relaxation, like a quadratic penalty term, if you want, or as a quadratic term. It could be done through like many different ways. We're going to stick with the quadratic penalty terms. And I will show you through computation and analysis that leads to improved convexity. I'm going to call it improved convexity. This is a loose term, right? You literally have a convex function or you don't, right? But I will show you what I mean by improved convexity, okay? And I think I can characterize it precisely mathematically, what I mean by that. And I'm going to study the well-posedness of this problem, okay? So let's start with the key idea. Now we're going to get into the weeds of how you formulate this method, okay? So we're going to start with, and I'm going to postulate everything in the frequency domain, because this is what I'll show you causes tremendous problems, right, for us. Now, the ideas I'm about to present to you have been extended to finite strength elasticity, have been used with anisotropic problems, viscoelasticity, and so on, okay? So it doesn't end here. Now, nonlinear problems, they have not been used too much in nonlinear problems, but because you cannot probably prove a lot of these properties, but it's unexplored. Maybe they have this similar method. All right, weak form, right? So we're going to start with the frequency domain, and I'm going to point to you at some. So this is basically, think of elasticity in the frequency domain, right? Elastodynamics, and you have here the first term that will lead to the conventional stiffness, the stiffness matrix and so on. You have what we'll call the mass matrix here, right? And this is going to be frequency for us, the gamma. Then something very important, and then the forcing. Now I'm going to point you to this term here. For us, right, when we formulate weak forms, usually that term goes away because the test functions vanish at the boundary. Actually, I don't know the boundary conditions. I cannot be sending the test functions to zero. So what we do is we construct what the boundary conditions should be for those test functions from the ground up. Okay, so and I'll mention a little bit more of that, but that term has to stay there. Because I say I know nothing about the boundary conditions, okay? So that's why you have the boundary minus the norm. Okay, the function spaces are going to be very important. So we're going to have the conventional, things that are subsets of H1. If I have Dirichlet conditions that I know, right, you're going to impose them. If a region of this surrounding just has data, you don't know anything, okay? All you know is you have data. Well, we have this space where we have the stresses that basically have to satisfy conservation of momentum, which is this equation, okay? That's all I impose for my stresses. And then I'm going to work with symmetric positive definite tensors for elasticity, right? So here are the elements, right? So we're going to postulate the inverse problem as an minimization problem. I'm building on the ground up to do that. So the elements. First, error in constitutive equation. So that functional that you see there, remember, the stresses and the strains are not connected. What you see there in our conventional formulations, you will say stresses is equal to the elasticity tensor acting on the strains, right? So right now I just say, okay, those two things are going to be independent fields for me. I weight that, okay, with the inverse of elasticity tensor. These things are just for making the problem nice, okay? So what I want is some metric of that discrepancy in the constitutive equations. So if you go back to 1981, when that I think it's 1981, the first paper, 1983, that where this was used as a posteriori error estimation, something that looks similar, not exactly like that, but that was the error indicator. Okay, so we're going to use it now for an inverse problem. Then that I'm going to augment it with a functional on the right, and I'm going to keep it abstract. That measures now the discrepancy of my observations. Here's where my observation center, where my data comes into play, right? And that kappa is just a user-defined parameter, right? That's going to play a very important role. Similar to the cone of regularization in inverse problem. All right, so once I have those elements, the way that we postulate the problem, this was basically where you spend, where this method begins into the application is by minimizing that functional. This augmented functional, this is why it's called modify error in constitutive equations. The original error in constitutive equations, you had just had the first term, epsilon, or calligraphic E. In 2007, Pierre Feisel and Olivier Ali extended this with that term, and they call it the modifier in constitutive equations. And since then, we've been using it that way, and that's what I'm going to analyze for you, right? So this here is what we solve as an optimization problem. Before I get into some actually very, I'm going to derive the equations actually. And I'm going to show you some simple ways to solve this, right? So as I mentioned to you, there are some things that I will need to assert. I didn't tell you what the test function space is. I'm going to tell you now how you get to that. That optimization problem, to solve it, you need to find the KKT conditions, right? So remember, I don't know the stress field, I don't know the displacement. The displacements are connected to the strain. Those two are connected in a conventional way. And I don't know the material properties, right? And I don't know the Lagrange multipliers, right? So this is my Lagrangian here, right? This is the only thing I know, fundamental governing equation, conservation of momentum, linear momentum, in this case. For now, you could impose other constraints, let's say, on these fields. Let's not do that for now, right? So this is a problem that is basically enforcing the governing equation. Take variations with respect to each of that, and you will get this system. This couple system of variational problems. The first one that you see here, right? This looks like my original wave propagation problem, except that I have the Lagrange multiplier in it as one of my variables. Okay. The second problem that you see here is again like a Helmholtz problem, but it's driven by the misfit in the data. For those of you who have seen adjoint formulations, this is the adjoint problem. In this case, it's self-adjoint. That's why you see this. That's the same operator. There's the difference, if you have ever seen how adjoint formulations are used to derive the gradient in optimization with PDEs, they're sequentially coupled. The forward problem is decoupled from the adjoint. The adjoint depends on the forward problem. So it's like a triangular system, right? And here they're fully coupled. And notice that all I did was go to the machinery of using this error in constitutive equation. But that result there is what leads to a lot of the good properties that this method has. The third equation here is not that important because we don't solve it like that. But together, they form a nonlinear coupled system of variational problems. Now, you can go at this one and try to solve those equations simultaneously with Newton's method, right? That will be a full space approach to the inverse problem. If you know George Beers or no Margaret, they did that with L2 type of formulations in a while. We're not going to do that. We're going to do adopt what is called a reduced formulation. Okay. By the way, I forgot to tell you that if you want to stop me and ask me a question, anytime, right? We have until 1.
Yeah.
Okay. I prepared this so that not to basically I'm going to overwhelm you with information, but in a short period of time, but not too short. Okay. So what I'm going to do now, those system of differential equations, variational problem, I'm going to put it in a way that I can give it to a optimization code and actually use optimization to solve for the one of the fields. So I'm going to condense out, or actually not condensed out, I'm going to decouple the problem so that I can express everything and a solution of a optimization problem in terms of only the shear, the elasticity tensor. Okay. So how do I do that? That's what is called reduced view of the inverse problem. So what I'm going to assume use is assume that I've solved the first 2 coupled systems of equation of variational problems, that are the forward and the adjunct, given an elasticity tensor, right? So that it just looks like a forward solve of a couple, if you want finite element problems, all right? Once I have that, I'm going to call that U sub C. So those U sub C, omega sub C, W sub C are fields that satisfy the forward and adjoint problems. Once I have that, then I can cast the objective of the problem just in terms of C, right? Because that's the only thing I don't know. Right. Given a C, I postulate U and W as functions of C. And then I can have just minimize that reduce objective, okay? So the reason I'm telling you that is because for implementation, this is the way we solve the problem. You give it to an LPF-GF type of approximation for the Hessian, we derive the gradient, and we solve it, right? Using line search or truss region. And that's how we do it. So this is what you see here in the last line, right? Also, I'm going to show you if you have an isotropic material, homogeneous, this problem admits a very simple decomposition if you think in an alternating directions. So if you fix, let's say that you say, okay, I know you start with a guess of the modulus, and then want to solve for the displacements of the stress tensor, that leads to a coupled system of equations. I just discretize it, put the algebraic system. So this is something that you'll be very comfortable with. What you see is in the diagonal, this is a knockdown Helmholtz operator, stiffness, mass, sorry, change of notation here from different presentations. That was gamma before, that's omega. Okay, that's the frequency. A stiffness matrix, right? Again, the same operator, Helmholtz operator. And this D is what we call the observation operator. This is what connects data to the model, okay? So if I solve this coupled system, now I have U and sigma, you can show that you can have a closed form expression for bulk and shear modulus once you have that from by minimizing the modifier in constitutive equation. So you can solve this in an alternating direction. Okay, so this is the algorithmic part of what I was going to show you. There is not a whole lot of that. This is the way that we implemented this originally. If you have ever studied alternating directions solutions, this is similar to Jacobi type of applications, right? In nonlinear systems, they can diverge easily, okay? So now the optimization approach where you use truss region line search, very robust. That's the way I solve everything these days. Now, why is this important? Because this brings me to a very important question analytically. Before I show you some very nice properties this idea has, let me interject now to ask a fundamental question mathematically. Is that system solvable and under what conditions? This is very important, right? For me to find a solution of C. So originally, we actually analyzed this discrete system. And this was Mark analyzed the problem, and we came up with this proposition which tells you under what conditions that system is solvable. And actually it's very striking, very nice when you find that. So it goes like this. That coupled system has a unique solution, and hence the solution is stable in finite dimensional spaces, if the kernel of the Helmholtz operator and the observation operator, the intersection of those is just trivial. What does that mean? Well, that either if you have eigenfrequency, like if you're driving at an eigenfrequency, meaning at a resonance, I told you that's one of the problems in elasticity, you couldn't solve the problem. You have a singular system. Here, because you have coupled system, you can have a singular block, and that's okay, right? Now, for that system to be solvable, what needs to happen is you need to be able to observe the modes of the system. That means the mode is not in the kernel of the observation operator. So if you're in the kernel of one, you cannot be in the kernel of the other. So if you have that, which is something very practical, right? I can always add measurements and actually solve the problem. Then that problem is inverted, the coupled system. I can use the implicit function theorem, and the forward Nigerian solutions are infinitely differentiable. Very nice things. I can use gradient-based optimization. That's the consequence. Towards the end of the talk, I'll show you the proof in Hilbert spaces for this. I'll sketch the proof. We will not do the proof. I'll show you that we prove in 2019, 18, this holds in infinite dimensional spaces, right? Okay, now, let me show you an actual problem that we solved with this, with experiments and everything. So with Mayo Clinic, we've been working on imaging elastic moduli. Here is where the bulk modulus disappears, because now it's known. We give it as a known to the code. We just solve everything in terms of shear modulus, but it's not known everywhere, right? Or it's nowhere known. The experiment was what you see in the middle here. I have a gel with a hard, stiffer gel in the middle. Have the transducer here, and there are 3 sets of experiments where we drive. Actually, I'm gonna tell you, we drive the radiation force at 3 different locations, and we acquire the displacement or velocity field that I showed you. The question is, can we reconstruct shear modulus? If you use conventional ultrasound, this is what you get, right? So if you try it really hard, you could probably see a silhouette of the inclusion around here. Actually, for the people online, I'm going to show you around here. I can probably see it because I've seen the picture a lot, but you may not see it. The question, that this is the motivation for using shear modulus. You will see that shear modulus, you can see this inclusion. So what we did was we did a reconstruction on these 3 configurations. Remember, I told you before that one of the problems is we don't know the radiation force. Well, there is an easy solution. Don't use it. Use a window that doesn't include the force, right? And that solves the problem. There was another thing I told you that I haven't dealt with. What about this issue with boundary conditions? I didn't tell you anything about that, right? I will in a second. For now, we are able to treat with the error in constitutive equation through the construction of what the test function space is. That comes naturally from the variations that I did. I just don't have time to go through all of those things. It comes there. You don't have to do anything else. You give it a field like this without boundary conditions. And also there are some mild conditions of when that will work. I will get to that. And you can solve the problem. Right? So I just use windows that don't include the radiation force. And those are the reconstructions that you will get. This was through truss regionalized search algorithms. Solve this, right? So if we quantify this by taking, we knew that there were only 2 materials here, right? And this is what you will get, right? These are the reconstructions that we got in the background and inclusion. This is the average, and this is the actual property measured with a machine, right? So this was a very successful, application of this, demonstrated through experiment. It got published here. So Santa Gosh was here, actually at one point as a postdoc with Marino Arroyo and UPC, right? So I hired him actually after leaving UPC. All right, finally, this is the last part of the talk, and I know that we don't have a whole lot of time, so I'm going to sketch some of the analysis, right? We're not going to go very deep. This is the paper. If you want to read it, analysis of very constitutive equations for time harmonic elasticity problems. We proved all the theorems there. I'm just going to show you that I'm going to highlight some of the properties of the methods through analysis, right? And then at the end, through some results. All right. So now what we're going to do is go to infinite dimensional spaces. So what I'm going to do is write the coupled system again. Let me preface everything. So remember, the inverse problem is a system of 3 variational problems that together they're non-linear, because even though you have a forward operator that is linear in the inputs and outputs, the material is not linear with respect to the inputs, right? Because they multiply each other. So now, once you remove the third equation, which is basically the equation that tells you that the variation with respect to the material has to vanish, we get into the reduced space problem. So the reduced space problem, remember, I need to solve that coupled system first, and then use it in an optimization framework. So that's why it's very important to understand the coupled system. So that's what we're going to do. We're not going to analyze the nonlinear problem, right? It's just the coupled system and ask for stability, existence, uniqueness, and stability of solutions, right? All right, so this is the coupled system. Anything that has a tilde is a test function, okay? So the fields that I don't know are W and U, right? So think of Lagrange multipliers in the observable field. So A, relate that to the stiffness matrix, if you want in your head. That is going to be the term that leads to that. B is the operator that would relate to the Helmholtz operator, nothing that is shifted by a map, by gamma square is the density, and then the inner product with the parentheses just basically the mass, right? And then D is related to the observations. Remember, that's the data. Okay. All right. And that capital D is the observation operator. We're going to give it some properties. We usually assume, well, I'll get to that. You need to now build the theory. You need to assume some things and then derive some of the things, right? So the first thing I'm going to tell you is this is a perturbed mixed problem, the structure of this, right? So if you look at the book by Brexy, right, in mixed problems, actually we use a lot of the results there to prove this already. And Germon, these are mixed problems, right? And we can use the theory that we know about mixed problems to analyze this. Now, it was not very straightforward, I can tell you, just using that and then getting the result. Otherwise, we wouldn't have published it, right? There were a lot of other techniques that we had to bring in from other fields. But basically, we are analyzing a mixed problem. G is an operator now that operates, that basically takes as an input a product space, right? So the mixed problem. And F, again, is the forcing term with all the fields in it. So if you put everything together, it just looks, this is what the operators look like. Probably not terribly important to go over that. And we're going to assume we're working with Hilbert spaces, right? Actually, Sobolev space, H1, and so on. All right, so here's the first lemma that we proved, which was that mixed problem, the operator is bounded below. That's very important, right? So bounded below will give you injectivity of the operator, okay? So we proved that, we're not going to go over that operator is injective. It's bounded below, right? If you have studied some of the analysis that happens in the INF sub conditions, basically what we're doing is proving the INF sub conditions for this system. They get translated to this boundedness below, right? If you have a symmetric operator, that's all you have to prove. You don't have to prove the other INF sub condition, right? That gives you the transpose, works with the transpose operator. So now, everything doesn't stay there, right? We have to characterize other aspects of this. This is where we got into the boundary condition issue. To generalize this, in fact, if you just had a very simple condition where you have Dirichlet conditions and all of that, it may suffice just to stay here, and you are done. If you don't have resonances or any of that. Now, the problem is we have incomplete boundary conditions, and we wanted to incorporate the situation where the operator, the Helmholtz operator was singular, actually had a null space. So this is the machinery that you need. Number one, characterize null spaces, right? So capillographic H is the null space of B, which is the Helmholtz operator, okay? And if you've done analysis at this level, you know that immediately in this couple systems, you need to look at the transport, the transpose operator as well as that, right? So we characterize also the null space of that. For what I'm going to show you, you need to keep that in mind, right? So those are just null spaces, calligraphic H and K. Z is basically a subspace that corresponds to all solutions, right? Of basically that give you resonances, basically, right? Solutions corresponding to resonance. Or if you have basically that's what it is, right? So I'm characterizing this Z here. All right. So here's the stability lemma that we basically prove given those conditions. So basically that you satisfy IMSUB conditions with a IMSUB constant beta, right? And that basically beta is characterized by the distance between, the minimum distance between the eigenvalues, if you want, of B and the driving frequency, which is a common result in Helmholtz equations. But to prove that here, it took a little bit more of doing. So notice this is a remark, right? So if U is equal to W, U is basically W is the test space, right? If you have the same, they coincide. That happens when you have basically a problem where you have Dirichlet conditions and non-Neumann conditions, and they cover the entire boundary. This is what happens usually when we are formulating forward problems. Then the problem is very nice, right? Like you basically get an IMSUB constant basically with C equals to 1. It's just the IMSUB constant that we know from Helmholtz systems. Something I forgot to mention that I need to bring into what is transpiring here. I'm skipping a lot of details. When you look at missing boundary conditions, we consider the following cases. That you may have Dirichlet conditions, Neumann conditions in the problem, but the sets, right, of the part of the boundary where they happen, they don't have to, the union of them doesn't form the entire boundary. They don't cover the boundary. So you may have part of the boundary where you have just observations, and then you don't know Neumann, you don't know Dirichlet conditions, right? And then you have Dirichlet conditions and Neumann conditions over other, right? Any combinations of those we analyze and it applies it. That part I'm not getting into because that's how the test function space, actually, you will find out that if I go to the analysis, what you find is that the conditions, the test function space over the boundary, there is the union of the Dirichlet conditions and data, they're zero. Usually what you get is the test functions vanish, but you have Dirichlet conditions, right? So in here, through the variations, actually, and going through the motions, you find out that they have to vanish where you have data as well. So hence, the test function space is usually a subspace of U because it has more conditions applied to it on the boundary, okay? It's a strict inclusion in the case where you have data and you don't have any boundary conditions. As a side comment, I didn't put it in the presentation because this is just a sketching of what we did there, right? I'm almost done with this. It's just to show you the results. So the assumptions for this to work, D is coercive. Think of using an L2 norm for the data. But, we have to put it in this sense. And experimental conditions are such that you either have that the Dirichlet conditions and the observations, right? Those two sets, the union is not empty, meaning you either have Dirichlet conditions or you have measurements. You can, somewhere in the boundary, you cannot be missing all of them, meaning all Neumann, we cannot solve, okay? All right, so if you have that, everything that I mentioned, you have a stable problem. Uniqueness of U, uniqueness of W, and stability, okay? Finally, let me just mention this. We could have skipped this, and I'm almost at the end. Mark is an analyst, one of the finest analysts you can find, and he has looked at perturbation analysis deeply. So he did that with this problem and he did a perturbation study remember the penalty parameter that I mentioned to you? That plays a fundamental role in the sense that as you change that parameter, you take it to infinity, right? That was the perturbation analysis it did. You recover the original method of error constitutive equations developed by LaCàN and co-workers. And if you take that perturbation and take it to the other limit of zero, you recover the original L2 problem, where the 4 and adjoint problems are uncoupled, which was a fantastic realization because we can show, we show that those, you're at the end in the middle of two spectrum of problems that we know really well. Okay, so this is the end, right? So one of the things I told you about the error constitutive equations, why we started working with this was because anecdotally, this has been shown that it led to problems that had improved convexity. What do I mean by that? The method, as we change kappa, right? There is infinitely kappa in between those two problems, lead to different objectives, as you see here. And as you increase that strength of kappa, going towards the error in constitutive equations, you start seeing this change in the objective function, in the reduced objective. So in the limit, when kappa goes to infinity, we can prove, actually this is in the paper, that you get a convex function, right? However, you cannot do this with real data because that kappa is enforcing the data. So if you take it to infinity, you basically strongly enforce Dirichlet conditions, which we didn't want, right? However, in between, we are getting something that has better properties than on the left, in the sense that there are regions, right? Sets of probably decreasing measure over which your functional is convex. We haven't proved what I just told you, but it looks like that. But in practice, there are regions of our parameter space where my optimization algorithms are converging to the global optimum. And for me, practically, that did it for this method, besides all the boundary condition stuff. So remember that problem? This is what happens with kappa. So this is where we started. In the limit of kappa going to zero, I recovered the original solution. And I started increasing kappa from the left to the right, to the bottom, all the way to the end. Something interesting that happens here, if I don't have any noise in the problem, as I increase kappa, I will keep the solution, the true solution of the problem unchanged. This doesn't happen in Tikhonov regularization as you change the Tikhonov step. So that we don't mix those. This is a very strong result, right? Like the fact that you don't move the minimizer, right? When you don't have any noise, is a very attractive property, right? You don't get bias, if you want, right, from this. When you have noise, you're going to introduce bias, but you can control it. All right. That's it. These are all the references. And we can have I can answer questions. If you're hungry, you can go to lunch or whatever. That's it. Thank you.
Are there any questions? I have one. You ended up working with a Helmholtz problem in a bounded domain. This is why you need the boundary conditions. Mm-hmm. So it's a very naive question. Why didn't you work in an unbounded domain with Sommerfeld at the infinity, no reflections? Because that's...
Yeah, you certainly can do that. Now, the issue is that you do get boundary reflections here. Yeah. But absolutely, for instance, in this problem that I showed you, you could put Sommerfeld conditions in those and go, and we actually did that. And you could solve it. Now, still the method performed better. With this, what you need to do is keep the Sommerfeld conditions in this method. That we didn't do. Yeah, but you can. Yes.
Questions? I don't know if there are questions among those who are connected online, but
I have a curiosity.
Yeah.
Mainly. When the space in which you seek the stress tensor, the sigma, this calligraphic S, is basically L2, divergence needs to be L2, and it's symmetric. Right?
Yeah.
At the discrete level, how do you construct this?
It just comes out naturally, right? Like, so put it this way, like that is just a statement of where it has to be, right? There is no construction per se. You can show that when you solve the equations, right, that we have, it comes out naturally with the symmetries.
Okay, so you don't need to pair appropriately the finite element space with
Not in what we did, no. And I think, you inherit probably, a lot of the structure that we were putting in the string tensor there.
Can I ask you, sorry.
Okay, go ahead.
Yeah, I was looking at some of your final slides, and the kappa, the choice of kappa was sort of not worrying me, but sort of piquing my interest because there were several orders of magnitude values of kappa. That obviously, you were saying if there is no noise, then in the data, then the solution will be the same regardless of the kappa. Inevitably, you will have noise. So what's the practical way of choosing a kappa, and what are the different possible solutions? Can you plot the solution you will get with different values of kappa for a problem with noise, obviously?
Yes, absolutely. We actually have a technique to choose kappa.
Okay.
At this point, it's heuristic, like Ticon, that we cannot prove optimality of those things. Meaning, we have a way to pick kappa. It follows the literature of inverse problems. So, for instance, you can use cross-validation. We use L-curve. Basically, an L-curve type of idea is you plot the L2 functional and the error in constitutive equation functional, right? And then plot that for solutions of the couples of the inverse problem, right? So basically, you choose the kappa for different kappas, right? You solve the inverse problem many times, and then this gives you an L-shaped type of curve, right? So you choose the one closest to the origin, because this is the place where you have this balance of the two errors, heuristically, right? In linear inverse problems, this has been shown to, like, if you have noise, right, that has really good reconstructions. The other way that you can choose it, if you know the noise level, you can estimate it, right? You can estimate noise level many different ways, and we've done that with ultrasound data. Use models of discrepancy principle. That has worked the best for us. And we have done control tests where we plot the true solution, add noise, estimate the noise, find kappa, and then see the actual true solution, how close it is among many other potential ones. And you're not optimal, but you're close to the truth. So that's the practical way.
Yes.
Do you need to impose some conditions for the shear modulus in the lower and upper bound?
Oh, absolutely. Yes, that's very important. So yes, you do put bound constraints in the optimization problems. Yeah. That's a must. The shear modulus can go negatively, and still you get, like, the system solved.
Any other question? If not, we will thank the speaker. But before that, let me say, if Barca wins tomorrow and reborns after all we will have to invite you more often then. So thank you so much.
Okay. I was telling Javier and I have a reservation for next year in a restaurant here in November, so I may be back.
You will be back.
Exactly.
And knowing the restaurant, you will be back.
Yes. I can, yes. This is something we are probably not working actively anymore. I told you about, I picked this.
Let me tell you that